So, for example, H2S. H2S is called hydrosulfuric acid, but most people don't call it hydrosulfuric acid. Most people call it hydrogen sulfide. Well, hydrogen sulfide is a name as an ionic compound, right? And so the same thing with HCl. HCl, most people don't call this hydrogen chloride. Most people call that hydrochloric acid. So there's no hard, set, strong rule, but sometimes there's a convention. So for example, if you're dealing with pure HCl, pure HCl is actually a gas. And so pure HCl, which is a gas, a lot of people will use the ion nickname, hydrogen chloride. But when we're dealing with a mixture like dissolved in water, so we take that pure HCl and dissolve it in water, and this is what AQ means. AQ means it's a mixture with water. And then, it's aqueous is what it stands for, and so aqueous HCl, we don't usually call hydrogen chloride because it's mixed with water. We call it hydrochloric acid, and so this is given the hydrochloric acid. Now, what if you can't tell? So I gave you one that you can't tell, HClO3. If we have HClO3 and there's no state there, what should we use? Should we use the ionic name or should we use the acid name? We should use the acid name. In general, if the state's not given, go ahead and call it the acid. And the acid here, except for like H2S. H2S, hydrosulfuric acid, it's just a weird name. Hydrogen sulfide is very common. And so HClO3, I would call this, what did you guys call this? Chloric acid. So I call it chloric acid, even though there's no state there. And so I wanted to mention that, but again, there's no hard set in stone rule. All right, let's go back to this. We have a quarter mole of ammonia. So how many ammonia molecules is this? It'd be a quarter of Avogadro's number, which would be 6,4, 1.25. We could use dimensional analysis. And so we'll just use this as the conversion factor. In a mole, there's 6.02 times 10 to the 23rd units. Just like a dozen of 12 units. Oh, 1.5. 1.505. Are we allowed that many sig figs? No, we're not allowed that many. How many sig figs are we allowed? 2. So we got to round this, which they didn't. They didn't round it. But of course, I want you to show me before rounding. So this is a one-step conversion, but it's the same thing. We got moles, so we got to get rid of moles. So we know that moles can go to this. We also know moles can go to grams. So for example, how much does an ammonia molecule weigh? And so ammonia, this is quick because if I have ammonia, I have 1 nitrogen, 1401, 3 hydrogens, 303, it's 1704. And so if I have those memorized, I can do these quite quickly. And so an average ammonia molecule weighs 17.04 U, which means a mole of the average ammonia molecules weighs 17.04 grams. And so what's 1/4 of that? Well, that's how much that would weigh. We're going to do that calculation. And so this is called molar mass. And so this one here is called the atomic mass. Except, this is not the average. This is the atomic mass of this. So rather than using atomic mass, we use isotopic mass, right? Or this one would be isotopic. This one with 12.01 U for the average carbon atom would be this. So atomic mass here, isotopic mass here. This one's a little different. This is called the molar mass. And the molar mass, it doesn't matter if it's isotopic or whatever else. This is the molar mass. It's the mass per mole of substance, whatever that substance is, specific isotope or however that. And so the molar mass, which is different than atomic mass or isotopic mass, is the mass of 1 mole of any substance expressed in grams per mole. The molar mass of any substance is numerically equal to the atomic molecular formula mass of that substance in atomic mass units. This is why Avogadro's number was chosen. So funny is so that we can maintain this relationship. The relationship is the atomic mass of carbon-12 is 12U. The molar mass of carbon-12 is 12 grams. And so it's 12, a single unit's U, a mole of those units will be in grams. Calculate the mass of calcium fluoride. Okay, what do they want? Do they want the formula mass? Do they want the molar mass? It doesn't matter because it's the same number. And so we'll just go ahead and calculate the mass. One mass would be the mass in U for formula unit. The calcium fluoride is ionic, so it forms a lattice. The other mass would be grams per mole of formula units. So now, calcium and fluorine, I don't memorize the masses for those. This is, hydrogen, carbon, nitrogen, oxygen. Those are the big ones to memorize. And so normally I would just look those up in the periodic table, which we can do. But first, I need the formula for calcium fluoride. And so let's see, let's go ahead and do calcium. What is the charge on calcium? Fluoride? Fluoride is charge. And so we'll need 2 fluoride. So the formula for calcium fluoride is CaF2. Now, what is the mass of calcium? Okay, so oftentimes we do this without units because the units can vary. And so I'll just write out, we look it up on the periodic table, I'll write it out to 2 decimal places. Now, how many rounding steps are you allowed? We're allowed 1 rounding step per calculation, right? But when we do these masses, I'm going to round it. I don't know if you guys can see that. Maybe I'll put it up here. So we look at the mass of calcium. If I go to 2 decimal places, this can make your life a lot easier because some of these go out to like 5, 6. But if we go to 2 decimal places, what would you use? Would you use 40.07 or 40.08? Now, officially we're only allowed 1, but when you're dealing with these atomic masses, we're going to go ahead and round it because if we use 40.07, then we're going to have more round off error than using 40.08. And so it's just going to average out. Sometimes we're going to round off error one way, round off error the other way. So we're going to use 40.08 for calcium. Now, I'm not going to put the units because the units, there are 2 units. When I see a 40.08, I read it in 2 ways. .08 means 2 things to me. It means 40.08 U per average calcium atom. Or it means 40.08 grams per mole of average calcium atoms. And so this is, I can use it either way, it doesn't matter. It depends if I'm looking at, individual formula units. But if I'm looking at individual formula units, then I need to know the isotope, right? And so it doesn't really make sense to do it this way. The only way it makes sense to do it is this way, because if we're looking at individual calcium atoms, will I find a calcium atom that weighs this much in nature? This is a trick question. Will I find a calcium atom that weighs that much in nature? The average.
Oh, the average.
You might if there's only 1. You know, an average of 1. So for example, there are some elements that only have 1 isotope. Do you know what they are? Well, we go to the table of isotopes here. Actually, if you want to know what's radioactive and what's not, this tells you. You know, this little graph tells you how stable the nucleus is. This is based on proton and neutron here. But this is not the isotope table I want. This is the isotope table I want here. Actually, that's not the isotope table I want. Here's the isotope. Okay. None of these are the table isotopes now. But maybe this one. This is too small. Well, basically, you need a table of isotopes. That there'd be plenty here, but and then you take a look and see, how many different isotopes are available. This is a table I'm looking for. And so, for example, hydrogen has 2 naturally occurring and 1 radioactive. The radioactives aren't listed. There are some tables that will list all the radioactive isotopes as well. Helium has 2, lithium has 2, beryllium has only 1. You see it's 100%. And so the average is very simple. This doesn't have the masses, I need the masses, but all beryllium atoms weigh exactly the same amount. They're identical. We don't have different ones. Boron, there's 2. So beryllium's 1 that doesn't have others. What's another one that doesn't have others? Fluorine. All atoms of fluorine weigh exactly the same amount. So, but what is it? It's off the periodic table. So all beryllium atoms weigh 9.01218 U. All of them. Fluorine, all fluorine atoms weigh 18.998. Sorry, it's hard to see you guys over there. Are there others? Sodium. This is, these are just pure observations. Of course, the nuclear physicists, they want to figure out how to predict these things. Can you predict what the next one will be? It'll be 100%? Well, you could if the theory were good and well developed. If we had a theory, we should be able to predict the next one. Not only that, we should be able to predict the number of naturally occurring isotopes. So for example, how many different xenon atoms are there in nature? 3, 6, 9. 9. So if we feed this in the mass spectrometer, we get 9 peaks, just like water. And we get 9 peaks there. Cesium. All cesium atoms in nature are this. And so what are the big ones? The big ones are, well, beryllium's not a big one. The reason beryllium is not a big one is beryllium is super toxic. So nobody likes to work with beryllium. The big ones are fluorine is a big one. And one other one's a big one. You should know. Do you see it? The other big one is phosphorus. Those are the most. Scandium is one, but how often do you see scandium? Cobalt is another. You know, and so phosphorus for sure, we'd like to know. And so there are a number of ones that don't have other isotopes. And so this is called the, well, this is only the abundance. I wanted mass and abundance. And there are tables like that. But so a lot of these tables are just excerpted. Anyway. So we did calcium. So it's going to be 40.08 U per atom or grams per mole. Since we're doing molar amounts, we'll do grams per mole. And then we'll do fluorine. Calcium, are you going to find any calcium atoms in nature that weigh 40.08 U? I don't know. The only way I'd know is if I look in the isotope table. Which I just changed here. But anyway, if I look. But if you know the big ones, what were the big ones? Phosphorus and fluorine. Then phosphorus has got to have multiple, right? But it doesn't. Calcium. Sorry, calcium's got to have multiple. Calcium is another common one, and it does have multiple isotopes. So you aren't going to find any. Now, when I go to fluorine, fluorine we'll just do to 2 sig figs. It's going to be 18.998. I'm sorry? It wouldn't be exactly 19. We wouldn't call it exactly 19. What would we call it? .00. And so we call it 19.00. And so the same thing here happens. 19.00 U per fluorine atom. And if I were to ask you the same question, can we find a fluorine atom in nature that weighs 19.00 U? Yes, all of them weigh 19.00 U, because they're all identical. All of them weigh. Could I say can you find a fluorine atom in nature that weighs exactly 19 U? No, you wouldn't find one. But, you know, if we rounded to 2 decimal places, we would. And so in other words, 19.00 grams if I had a mole of fluorine atoms. So if I had an Avogadro's number, 61022 times 10 to the 23rd, fluorine atoms is going to weigh 19 grams. So that breaks up. What is 6.022 times 10 to the 23rd? That means if I had 6, now I need 23, move the decimal place 23 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So if I move it 23 places, and so I'll count it out, 1,000, million, billion, trillion. So we'll go to trillion here. 1,000, million, billion. We'll go to a billion here. So if I had 602 billion trillion fluorine atoms, if I had 602 billion trillion fluorine atoms, it would weigh 19 grams, 19.00 grams. All right, so all I do is add it up now. So it's 2 times 19, which would be 38. 38 plus 40.08 gives me 70.08 grams per mole. So let's check that. Yeah. Oops, 78. 38. Plus 40, 78. So 78.08 grams per mole to 2 decimal places. All right, this illustration is just to show you approximately what a mole of substances is. So the average iron atom weighs 55.85 U per atom. A mole of those atoms would weigh 55.85 grams, and a mole of atoms is 602 billion trillion atoms. And so this is about 602 billion trillion atoms here. Just weighed out on balance, it's 55.85. So if I have 602 billion trillion atoms, that's what it looks like visually, and this is how much it weighs. Aluminum weighs a lot less, it's a lighter atom. It's 26.98 grams per mole. So that would be 602 billion trillion atoms of aluminum. This would be 602 billion trillion atoms of mercury. This is sodium metal here, 23 grams. Copper, 63.5 grams here. Nitrogen gas is 28 grams. So that would be 28 grams of nitrogen in that balloon. And that would be 602 billion trillion atoms. There's a lot more empty space there. The balloon looks a little small. 602 billion trillion nitrogen atoms usually occupies the space of 24.5 liters. So that balloon looks really small. It should be 24.5 liters. We also have this. Like if I look at 1 copper, 1 sulfate, and 5 waters, then the mass of that is 249.7 U. If I have a mole of those units, it would be 249.7. Here's my water. This is 18 milliliters of water. A mole of water. Mercury oxide, oxalic acid. Oxalic acid dihydrate.
I know it's probably not topic, but just mention aluminum. Why is that? You know, when you put aluminum in the microwave, like it deflects I guess heat and other metals don't.
You put aluminum in the microwave?
Yeah. No. But I'm saying like.
Did it spark?
Yeah.
Why does it spark? We're going to talk about that. Talk about that.
Nah, I didn't.
Basically, because microwaves will excite electrons, and it's not just aluminum, but if you have ceramics with big metal atoms like cobalt in there, cobalt has a lot of electrons, and those electrons get excited and you get very hot. And those electrons get excited, they can introduce some anions. But we're going to talk about that pretty soon. All right, so let's try this next one. You have a experiment reaction that requires 0.0360 moles of barium chloride. How many grams of compound do you measure out? Well, this one might be a little basic, so. Of course, we need the formula. Formula for barium chloride is BaCl2. And then we gotta add them up. Chlorine is 35.45. Barium is, look it up on the periodic table, 137 point something. Is that right? Oh, this is wrong. This cannot be the molar mass of barium chloride. Barium alone is 137.33.
So maybe if you hit
Yeah, maybe if I did the next key. Oh, there it goes. Barium is 137.33. You go 2 decimal places. 2 chlorines, each 35.45. 28.23. That would have given me 5 sig figs easily. Don't do this thing where they screw things up like this. Just go 2 decimal places for all your molar masses. It'll keep it consistent. Don't do this 1 decimal place thing. And then we have the conversion factor. So this is a simple single-step conversion. You know, it's a mole to gram conversion. The other one earlier was just a mole to number conversion, number of units using Avogadro's number. is a mole to grams used for molar mass. Those are two very common conversions. This is probably one of the most common calculations is gram to mole or mole to gram conversion. We can look at it in, this is called a mass like this. So if we have the number of units, we can convert it to moles using Avogadro's number, 6.022 units per mole. Just invert it. 1 mole, 6.022 units. And so here we're converting from units to moles, number of units to moles. And then we can convert from moles to grams using the molar mass over here. Or, you know, these are very common calculations. Grams, we can convert to moles using the molar mass, you know, invert it. And the moles to number of units using Avogadro's number, which is abbreviated N sub A number, Avogadro. So N sub A stands for Avogadro's constant or number. And you should memorize it, 6.022 times 10 to the 23rd. And MM stands for molar mass in grams per mole. Okay, molar mass is different than molecular mass. Molecular mass is the mass of a single molecule. Molar mass would be the mass of a mole of molecules or whatever else you're looking at. This is called stoichiometry. Have you ever heard of stoichiometry? Mm-hmm. You know what stoichiometry, the definition of stoichiometry is? Stoichiometry is just quantity relationships. You know, so we're relating some quantities to other quantities. And so quantity, just quantity relationship. And so the stoichiometric pattern, we don't really, you know, this first one I know. This is like a gram to mole conversion, mole to number conversion. Those are stoichiometric relationships. And so it doesn't, I don't get caught up. Like, for example, I don't memorize a certain pattern in that sense. And so maybe that makes it more difficult, but if you memorize one single pattern, then you aren't, then you're going to have to memorize a ton of patterns because there's so many different branches that you can go off. But anyway, I just do this using dimensional analysis. And so that way I don't memorize a pattern. I just try to go with whatever comes up. So we have 3.2 times 10 to the 24 molecules of sulfur tetrafluoride. And so using dimensional analysis, that's my starting point here. 3.2 times 10 to the 24 molecules. Okay, then of sulfur tetrafluoride. Sulfur tetrafluoride, what's the formula for it? F4. Okay, then I need something that gets rid of molecules. So I need something that gets rid of molecules or molecules of SF4. And so do I have something that gets rid of molecules or molecules of SF4? If I have something that gets rid of molecules, for example, if I have 6.022 times 10 to the 23rd of any molecules, that's equivalent to a mole of whatever molecules. Oftentimes this mole of molecules is just called moles. And so molecules cancel, and that gives me moles of SF4. And so now I have moles of SF4. I could have gone to mass. I know that the mass of SF4 molecule, the average mass of an SF4 molecule is the average mass of sulfur plus 4 times the average mass of fluorine in U. And so I could have went from here, molecules, to U. And so there's a lot of different paths you could go. Depending on the path, you know, you might end up at a dead end, you might not. if I went from molecules to U, I would get to the same answer eventually. But I already know which way I'm going because we've done this calculation many times. So mole of SF4, well, how much does a mole of SF4 weigh? And so we look it up on the periodic table. Sulfur is 32.07. Fluorine is 19.00. And we have 4 of those times 4. And so we just add it up. 108.07. 108.07. And so we got 5 sig figs, which is fine, but always go 2 decimal places. And so that many grams of SF4 in 1 mole. And so the moles of SF4 molecules cancel out. We're left in grams. So let's see what they did here. All right, for fluorine, for sulfur they used a little different than what I used. So I used a base on periodic table. But they did a mole to, well, do you see an error here? I see an error. I'm sorry? Yeah. Well, I see a couple of errors. One error is they got the fluorine mass just at 2 sig figs. It's wrong. And then this should be rounded to 3 sig figs. So that's one error. What's another error? Well, sulfur. Let's take a look at sulfur. It's not really an error, but let me just show you. Sulfur is 32.0. Can you guys see it in the back? 32.066. So if we go to 2 decimal places, it should be 32.07. So sulfur should have been 32.07. It's okay. I see a more significant error though. This is the error I see often on tests. Is a mole the same thing as a molecule? No. A mole is not the same thing as a molecule. We have 3.2 times 10 to the 24 molecules. What is it saying? Yeah, don't ever abbreviate molecules using the same abbreviation as mole. No, we don't usually abbreviate molecules. We'll just spell it out so there's no confusion. And this is impossible. How can 1 mole of SF4 be equivalent to 6.022 times 10 to the 23rd moles? Like, okay, oh yeah, I have 12 eggs, which is equal to 12 dozen eggs. That's what they're saying. 12 eggs is equal to 12 dozen eggs, or 1 dozen eggs is 12 dozen eggs. It doesn't make sense, so unfortunately. But it's okay because what we need to know this well enough that we can find errors and fix it. They get the right answer, I guess, or close enough. All right, so that's one thing we can get. There are other things we can get from the formula. The formula tells us the composition, right? But it tells us the composition as an atom or mole ratio. We have 2 types of formulas that we're dealing with. We have the molecular formula and what was the other type of formula that we're dealing with? Empirical formula. both of these are called formula units. But they describe the composition. Both of these tell us the composition. And we call it an atom/mole ratio. Because sometimes we're dealing with individual atoms, sometimes we're dealing with moles of atoms. And so the way it goes is like this. So H2O. H2O says there are 2 atoms of hydrogen for every atom of oxygen. So 2 atoms of hydrogen for 1 atom of oxygen. It could also be a dozen. You know, there would be 2 dozen hydrogen atoms for every 1 dozen oxygen atoms. Or it could be moles. 2 individual atoms is too small. Dozen is too small. We want moles. Moles is big. And so it could be 2 moles of hydrogen for every 1 mole of oxygen. And so we're most likely interested in the top and the bottom ratio. And so this is why we call it an atom or mole ratio, because these are the most useful for us. And so, okay, then we have an atom/mole percent. If we're looking at an atom or mole percent, then hydrogen, there's more hydrogen than there's oxygen. In fact, water would be 66.7% hydrogen, rounded to 3 sig figs, and 33.3% oxygen. Okay, but this, again, this is called an atom or mole percent. And so that means this: if I have 100 atoms of oxygen, you know, how many atoms of hydrogen do I have? 200. If I had 100 molecules of water, how many atoms of hydrogen and how many atoms of oxygen do I have? If I had 100 molecules of water, I would have 200 atoms of hydrogen and 100 atoms of oxygen. So this is how we use this, atom percent. Now we do the exact same thing. If I had 1 mole of water, okay, well, if I have 1 mole of water, it weighs 18 grams. If I have 1 mole of water, how many moles of hydrogen do I have? I have 2 moles of hydrogen and 1 mole of oxygen. 2 moles of hydrogen weighs how much? 2.02 grams or 2.016 grams. 1 mole of oxygen weighs 16 grams. So if I have 1 mole of water, that's 18.02 grams. Out of that 18.02 grams, 2.016 grams of hydrogen. And so let's take the mole percent. So 1 mole of H2O is equal to 18.02 grams of H2O. And if I have 1 mole of H2O, then I have 2 moles of H. 2 moles of H is equal to, here I'm going to take it to 3 decimal places because I want 4 sig figs. I get 2.016 grams of H. If I have 1 mole of O, I have 16.00 grams of O. And so now I can do this. I can do 2.016 grams of H for every 18.02 grams of H2O times 100%. And this is going to give me the percent by mass hydrogen, which comes out to about 11% hydrogen. And so water, even though water consists of 66.7% hydrogen by atom, it only consists of about 11% by mass. And then it's mostly oxygen, because oxygen weighs a lot more. There's 16.00 grams of oxygen for every 18.02 grams of H2O. And then we times it by 100%, and then we get what's called the mass percent. And so this is a percent by mass. This is a percent by atom or mole. And so in composition, we're always talking about percentages. Are we talking about the mass percentage, or are we talking about the mole/atom percent? And so it's critical to know which percentage you're talking about because the numbers are going to be totally different, based on this. And so this is percentage by mass. And so all we need to know is, if we want to know the percent A, then we just need to know the mass of A over the total mass. The mass of A, well, the mass of hydrogen over the total mass of oxygen over the total mass. This would be A, this would be B. Okay, so we can calculate the mass percentage of fluorine and calcium fluoride. If we do that, this is the way we do it. The way I think about it is, how much does calcium fluoride weigh? Well, a mole of it weighs 70.808 grams. Well, how much fluorine is in there? Well, there are 2 fluorine atoms, there's 2 moles of fluorine. Each mole of fluorine weighs 19, so times 2 is 38. And then there's 38 over 78, which is about 50%. So it's 50% by mass fluorine, roughly. But by atom or mole, it's 66.7% because 2 out of 3 atoms are fluorine. So let's take a look at that color. There's still around 50% fluorine. What do we got? 48.67% to 468. Is it time yet? Yeah. All right, let's stop here.